In 10.2, we learned the calculus of parametric equations. So we're going to learn how to take derivatives, first derivatives and second derivatives. We're going to learn integrals, finding the area inside of a parametric curve. And finally, we're going to learn about arc length will be the very last thing. Okay, so let's get into it. So parametric equations, if you remember, it's two functions, one for x, one for y, usually in terms of t. X equals f of t, y equals g of t. So how would we go about taking derivatives? And these are, it's kind of interesting the way some of these things play out. Much simpler in one sense than you might think. So here's a theorem. The derivatives of curve C at any point xy are dy over dx will equal, you think, okay, well, dy over dx, so we're still thinking like a slope, the change in y over the change in x. But now there's this other, variable t involved. Well, all we got to do is take dy over dt, put that in ratio with dx over dt. And in one sense, we could imagine those dt's canceling out. But, there you go. So take the derivative of y divided by the derivative of x, and you'll have the derivative with respect to t, the first derivative. The second derivative is kind of interesting and is definitely not intuitive. So it turns out for the second derivative, you take the derivative of your first derivative, right? D over dt applied to dy over dx. That would involve t's, by the way. But then you're going to go further and divide that a second time by dx over dt. The same thing you had back here, the first derivative of x. Now that's really strange. Again, who would see that? You would think maybe just the numerator. Why do we divide by dx over dt a second time? Here's why. Just a very, very brief proof, but this sort of thing is going to be insightful when it comes to the integrals and all that also. So I show it to you. The second derivative, so think of it as taking the derivative of the first derivative, but we're used to thinking d over dx applied to dy over dx. But now, just the same way as we did this first derivative back here, we're going to think of d over dx as two independent pieces. D over dt over dx over dt. And that's where that dividing by dx over dt comes in again. So we applied the derivative with respect to t to our first derivative, but then because of that over dx, we need to divide by our first derivative of x with respect to t. Let's see just a quick example here with some polynomials. Get used to this, make sense of it. How does this play out? So before we get into more difficult examples, I've got this one for us, and let me go ahead and cover up this side for now. Okay. How about x equals t to the third, y equals 1/2 t squared. Let's find the first derivative. So we need to find the derivative of y divided by the derivative of x. So the derivative of y, well, that's just t to the first, right? Derivative of x, 3t squared. So I take the dy over dt, put it over dx over dt, t over 3t squared. It turns out it's 1 over 3t. There you are. Kind of nifty little style there, right? Okay, now what if we wanted to find the second derivative? That's where things get more interesting. So I'm going to take the derivative of this with respect to t, but then divide it by that again. So the derivative of 1 over 3t with respect to t, well, if you think of it as t to the negative first, negative t to the negative 2, so negative 1 over 3t squared, but then that gets divided by 3t squared. So here's the whole thing, the second derivative, negative 1 over 3t squared over 3t squared again, and that ends up being negative 1 over 9t to the fourth. there's your second derivative. Okay, so we kind of got a feel for, you know, how it all plays out. And it is all in terms of t, right? Even though this is dy over dx, our answer has the t. All right, just briefly, I wanted to compare this to doing the derivative in the more familiar style. So if you might recall that example back from one of the early examples we did in 10.1 when we were graphing, we found the Cartesian version of those parametric equations is y equals 1/2 x to the 2/3. Maybe you remember that. So let's take this derivative and just compare here, okay? So doing the derivative the way we're used to, multiply the 2/3 down, okay, 1/3 x to the negative 1/3. Think of that as 1 over x, 1 over 3 x to the 1/3, like this way in the denominator. How are these two connected? Hey, isn't x t to the 3rd? So that makes t equal to x to the 1/3. X to the 1/3, that's 1 over 3t. There it is, same thing. Hey, why stop there? Let's confirm that second derivative. So think of y prime as this. So just using that, getting y double prime, negative 1/9 x to the negative 4/3. Okay. Maybe putting that in the denominator, negative 1 over 9 x to the positive 4/3. We want to confirm that's the same as negative 1 over 9t to the 4th. Well, x to the 4/3, x to the 1/3 is t, so x to the 4/3 is t to the 4th, negative 1 over 9t to the 4th, and we got it. Pretty cool. If you really wanted to go further, you could even look into the graph. You know, we did the graph with the orientation and the values of t, and you know, when is the derivative positive, when is it negative, you know, for comparing slopes increasing and decreasing. You could look at concavity. Right here, it's always concave down, so that second derivative is always negative. You could go further if you wanted to. I'm going to stop right here. Let's get into our first big example. We're going to find the equation of the tangent line at this point, root 2 over 4, for this set of parametric equations. X equals cosine cubed theta, y equals sine cubed theta. Both of them are cubes. The equation of the tangent line. Okay, so we'll need the derivative, and then we'll have to figure out a way to evaluate that derivative at our point. And that's actually going to be most of our discussion. But okay, one thing at a time. Let's get the derivative first off. So we need the derivative of y divided by the derivative of x. And I've just done, I think, all of it right here. Let's just go for the whole thing. So dy over d theta, well, we got a chain rule, right? 3 sine squared theta, cos theta. Sure, derivative of x. Similar, 3 cos squared theta, negative sine theta. Clean that up a bit, negative 3 in the front. And we take the ratio, so we put the dy over the dx, dy over dx. Here, lots of things cancel out, so that's nice. A cosine and a sine and 3's. dy over dx equals negative sine theta over cosine theta, which you might even go a step further and just call that negative tangent theta. Okay. So we've got the derivative. No big deal there, some nice cancellation. Now, in order to get the slope of our tangent line, we need to plug in a value of theta. But here's the thing. The point is an xy point. They didn't tell us the value of theta that goes along with that x and that y. We're going to have to figure that out on our own. And that takes a little that's kind of the newness here more so than the derivatives. What is theta at that point? Root 2 over 4, root 2 over 4. That's my x and my y. So here's what I'm going to do. Remember, x equals cosine cube theta, y equals sine cube theta, those original parametric equations. I'm going to take that value of x, that value of y, we're going to figure out what theta is. And they'll need to agree. So let's look. We'll kind of do this side by side. I'll zoom in a little bit. I'm going to make this a little bit bigger. Okay, so I'll plug that x value, that y value. Now this is challenging, right? I mean, we've got a cube and a cube. Here's what we want to do. I cannot take a cube root over here very easily. But I realize, hey, I've got a 4 in my denominator. It would be a lot nicer if it was an 8, so I could take a cube root. So let's multiply top and bottom by 2. And I'll even do that over here also. Let's think of this as 2 root 2 over 8. Then when I do my cube root, at least my denominator will be a whole number. Same thing over here. Turns out though, when I do the cube root, not only do I get a nice denominator, even the numerator. 2 root 2, isn't that root 2 cubed? Because when you multiply it twice, you get that 2 right there, and there's the third one. So when I do my cube root, it's root 2 over 2, root 2 over 2, because that numerator's cube root is root 2, and of course the denominator of 8, cube root. Okay. Now let's just think, what value of theta will produce this with cosine? Well, do an inverse cosine, and you'll realize it's pi over 4. Similar over here, do an inverse sine, you'll realize it's pi over 4. So they agree. And we can just take that acute angle. There are more solutions here. There's infinitely many solutions if we add 2 pi. But let's just go with pi over 4. That'll be the first time it happens for positive values of theta anyway. Perfect. So we've got the value of theta. We can plug that into our derivative. And okay, let me try not to show you too much. So I'm going to take pi over 4, plug it in, negative tangent pi over 4. That turns out to just be -1. So there's the slope of my tangent line. And let's go ahead, I'll show you the whole thing. Now we need the equation. So I need point slope form, my x value, my y value, my -1 slope. Clean it up a little bit. I get y equals -x plus root 2 over 2 as the equation of my tangent line going through that point. I invite you, go back, graph all this in Desmos, graph those original parametric equations, x equals cosine cube theta, y equals sine cube theta, graph that tangent line right there, just confirm that it all works. Let's stop this video right here. I'll see you in the next example.